The law of universal gravitation, introduced by Sir Isaac Newton in 1687 in his work Philosophiæ Naturalis Principia Mathematica, is a cornerstone of classical mechanics. It describes the gravitational force, the fundamental force responsible for the attraction between all objects with mass in the universe. Statement of the law. The law of universal gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Mathematical representation. The law is expressed mathematically as F equals Gm1m2r2F equals G backslash frac m_1m_2r squared, where F, the gravitational force between the two objects, measured in newtons, n. G, the universal gravitational constant, which has a value of 6.674 times 10⁻11 nm2/kg 26.674 times 10 caret -11 \text nm caret 2 \text kg caret 2 m, mass of the first object in kilograms, m2, mass of the second object in kilograms, r, the distance between the centers of the two objects in meters. Key features of the law. 1. Proportional to the product of masses. The force of gravity increases with the masses of the two objects. For example, if the mass of one object doubles, the gravitational force also doubles. 2. Inversely proportional to the square of the distance. The gravitational force decreases rapidly as the distance between the two objects increases. Specifically, if the distance is doubled, the force becomes 1/4 of its original value. 3. Mutual force. The gravitational force is mutual, meaning both objects exert equal and opposite forces on each other. For instance, the Earth pulls on the Moon with the same force that the Moon pulls on the Earth. 4. Long-range force. Gravity acts over vast distances without requiring any physical contact between objects. It is the dominant force on astronomical scales, governing the motion of planets, stars, and galaxies. The gravitational constant, G. The universal gravitational constant, G, is a proportionality constant that makes the units in the equation consistent. Its value is approximately G equals 6.674 times 10⁻11 nm2/kg 2G equals 6.674 times 10 caret -11 \text nm caret 2 \text kg caret 2. This value was first measured experimentally by Henry Cavendish in 1798 using a torsion balance. Applications of the law. The law has far-reaching implications, explaining both terrestrial and cosmic phenomena. 1. Terrestrial applications. Weight. The weight of an object is the gravitational force between it and the Earth. W equals mg. W equals mg here. Gg is the acceleration due to gravity, 9.8 m/s 29.8 \text m/s caret 2 on Earth. Free fall. Objects fall to the ground due to the gravitational attraction of the Earth. 2. Astronomical applications. Planetary motion. Newton's law explains why planets orbit the Sun. The Sun's gravitational force keeps planets in their elliptical orbits, as described by Kepler's laws. Tides. The Moon's gravitational pull on the Earth causes ocean tides. Orbital mechanics. It forms the basis for calculating satellite orbits and planning space missions. Formation of celestial bodies. Gravity causes matter to clump together, forming stars, planets, and galaxies over time. 3. Global Positioning System, GPS. Gravity affects the orbits of GPS satellites, and precise calculations of gravitational effects are essential for accurate navigation. Limitations of Newton's law. 1. Extremely strong gravitational fields. The law breaks down in extremely strong gravitational fields, such as near black holes, where Einstein's general theory of relativity provides a more accurate description. 2. Quantum scales. On microscopic scales, gravity is not well explained by Newtonian physics and must be reconciled with quantum mechanics. Relationship with Einstein's theory of general relativity. While Newton's law is an excellent approximation for most scenarios, Einstein's general theory of relativity offers a deeper understanding of gravity. According to Einstein, gravity is not a force but a curvature of spacetime caused by mass. However, for weak gravitational fields and slow-moving objects, Einstein's equations reduce to Newton's law. Visualization. To better understand the law. 1. Imagine two spheres, one representing the Earth and the other the Moon. The force of gravity pulls them toward each other, keeping the Moon in orbit around the Earth. 2. If the Earth's mass were doubled, the gravitational force between the Earth and the Moon would also double. Significance of the law. Newton's law of universal gravitation unified the motion of celestial and terrestrial objects under a single theory, marking a revolution in scientific thought. It paved the way for modern physics, astronomy, and space exploration. By describing the fundamental interaction that governs the motion of objects in the universe, this law remains a cornerstone of science.